Okay, is the microphone working? Okay, so yeah. No. Yeah, thanks first of all to David for putting up some pressure for me and to talk. And thanks to the organizers for having me in this session as a kind of a slightly off-topic computer scientist. So I'll be talking about some work we're doing in the previous years with PhD students of mine on parallelization and software concepts for primarily dynamically adaptive mesh refinement with using triangular grids. And the target application is tsunami simulation in, featuring a joint project with.
You have to change it, the refresh rate.
Okay. Oh, come on. Where do I do this? This one?
Yeah.
Hi. 60 hertz?
Yes.
40?
No, it should be 60. Is it not on there?
What it says it's fixed 60.
Should change this.
The resolution.
Yeah, try that one.
Okay, so let's take the time until it fails again. Okay, so as I said, topic is still there. Motivation is, should probably better switch to the laptop, right?
Yeah. There is a center laptop, but yes,
change the resolution so you can get it to work.
Another laptop.
Would you just rearrange? I will just attach my.
Whilst we're waiting, can I just make a quick announcement? I heard very recently that you've just been funded to have a network in climate modelling using mathematical methods. This is an ESRC funded network, and that network starts in the end of this year, and as a result we'll be having a series of workshops funded by ESRC looking at mathematical methods of climate modelling. So I'm going to let you all know about when these are happening, so hopefully you can become part of this network. It's called ClimateNet, and I'll be sending more information to the organisers. So these will be workshops, there'll become a couple of workshops a year, and this is a collaborative project with the Hadley Centre and various other climate modelling centres.
Hopefully we're nearly there. While we're having a brief break, I'm sitting in a position where I have a great view of that screen up there, and they keep flashing up the end of week reminders. So if you are leaving the centre this afternoon, please do all the things that are on the screen and don't go wandering off with their keys or cards or other things that will cause bureaucrats to worry.
Okay, sorry about this. So usually my laptop is well behaved, but probably not.
Yeah, that's just very well behaved. I think it's the thing up there.
Okay, so I was about to start with motivation. So our motivation is the kind of a scenario provided by Tsunami simulation for parallel and adaptive mesh refinement. So what we want to do is, if we have such a propagating tsunami wavefront, we will try to adapt on the wavefront, the propagating wavefront, and if you kind of try to really keep the highest resolution along the front, you will have to update the mesh in every time step. Otherwise, you risk that you run with a shop front into an under-resolved area. So this would be this requirement below here that you want to be able to do remeshing in almost every time step. And even more so, there's a scenario for refinement when you want to simulate inundation. Like in this example, it's really probably only an illustration from a Cartesian, computed by a Cartesian code, but also at the coastlines, you would like to do a very fine resolution, but of course only, or preferably only once the wave actually arrives there. So the kind of computational setting and parallel AMR setting, that how we view it on that is kind of guided by these five issues, principles. So by the kind of challenges this application poses for grid refinement and coarsening, frequent remeshing, that we have a substantial change of the problem size also during simulation. So you've seen, I think, such a plot that Jörn has showed us, that there's kind of reaching a plateau. You have an early situation where the simulation size rises, then you reach a plateau, and then if you want to simulate inundation, you probably have another such a rising step. So that would be challenges from the grid refinement part. You have challenges from the architectural side. So what I like to focus on there is the so-called memory wall, so that the growth of CPU speed is really outrunning heavily that of memory speed. So if you look at the recent 20 years or so, memory latency, kind of the first access to a remote and kind of random access byte in a word in memory, so that speed has improved by about 5% per year, compared to a 60% improvement or doubling about every 1.5 years for CPU speed. So that memory gap that you have is kind of doubling every maybe, let's say, 14 or 15 months. And so when you want to worry about speed for codes in the next 10 years or so, or algorithms, you definitely want to minimize the memory requirements and the memory footprint, so the amount of memory you access during your simulation. And also you want to improve stuff like locality properties of your access patterns. You want to go to stream access, so that you are actually limited by memory bandwidth and not by latency. So it's kind of improve the entire memory behavior of your algorithms. There's of course a huge trend for parallelization. So there we want to focus on dynamic load balancing naturally, due to that changing computational load that we have. Interesting problems that arise in such methods is maybe if you use local time stepping. So that's nothing that we started yet, but what we would like to do in the very near future. There's huge challenges for building the software. So Robert has actually talked a little bit about that. So the Dune approach, I think they're much farther than we would be in that direction. And well, our approach to tackle these things is kind of structured around structured adaptive grids, because we We believe that any structure is likely to help you in tackling these challenges. And so we are based on our newest vertex bisection refinement. We are using Sierpinski space filling curves. Jörn has told about this already a bit, and I will give more details on that. How we exploit this for cache and cache locality and parallel efficiency. Yeah, and what I will tell about, especially today, is a comparison of maybe classical and more novel parallelization approaches for this. So first, a quick look at the AMR scheme. So I think this basically very schematic. So you start with initial triangular grid. So this is only one grid cell shown here, or one coarse grid initial cell. And then by recursive bisection, you would refine the grid, and you can you could describe or visualize this refinement by a corresponding binary refinement tree as shown to the left. This refinement can be adaptive, and which gives you such an unbalanced refinement tree. And if you want to throw in the Sierpinski curve is a sequential order on such a triangular grid, and the interesting thing is that it corresponds with a binary tree. That in the case, if you do a depth first traversal of this tree, you will exactly traverse the grid cells in this Sierpinski order. So that is so in our later algorithm will be strongly based on traversals, or it will be entirely built around traversals of this binary tree. But I also have to say at this time that we do not necessarily build up that tree, or do not necessarily have recursive traversals as our kind of coding scheme. But the real idea is to have this traversals and tree traversals as the guiding principle. In principle, this could give you minimum requirements of something like 1 bit per tree node, but because the kind of neighborship properties of the grid cells, where they are in space, and so this is all encoded in the tree structure. In practice, you probably want to invest some more bytes of memory just to be more efficient, to have it more handy in programming. But you come by with really very low memory requirements, and that is, in my opinion, one of the largest advantages that this method shares, of course, with quadtree, with octree, and any kind of these tree-structured refinement approaches. What we especially have to solve for our grid refinement is, for example, if you want to have conforming grid refinement, we have to make sure that if we refine such a grid, information on this refinement is propagated to the adjacent cells, so there can be such a refinement cascade actually. And that refinement cascade can actually transfer in the direction of the curve, but also backward in your traversal direction. So this is a very early part of the traversal, and here's kind of the late part of the version. So what you have to do is do several traversals of your grid to propagate this refinement information, and it actually requires exchange of data between neighboring grid cells. And for that exchange, and of course you have the same exchange when you want to do flux computations. You need the unknowns in neighboring grid cells to compute fluxes for finite volume or discontinuous Galerkin methods in the grid cells. And if you want to accumulate residuals and finite element methods, you would have to combine information from adjacent cells to maybe collect a residual value on such a vertex. So this really comes down to exchanging data between grid cells that are neighbors in space but can be far apart in terms of the traversal order. And we solve this by a so-called stack property. That means, so if you see this blue traversal order along the space filling curve, you can see, for example, for these 3 edges, if you access these 3 cells, you see that the edges are accessed in ABC order, in upward order, and when you traverse them downwards on the other side, they are traversed in backside order, so you get a last in, first out principle, which is exactly a stack. And you have actually 2 stacks two systems of stacks, a green one and a red one system, which correspond to the left-hand and right-hand side of the space filling curve. So our final processing scheme is in the end such a thing. So we will stream in grid cells along this space filling order, and we also will stream in edge-based and vertex-based data as such streams, and they are kind of streamed in a first access pattern. So the first time I access these things, I have to read them from the stream, and they are explicitly stored in that order. I will have an intermediate system of a system of stacks that will do intermediate storage, that will exchange the values between adjacent grid cells. And once I'm finished with the processing of an edge, of a vertex, of a cell, I will write it to an output stream. And this is actually a last touch order that I'm doing. When I last touch a vertex or an edge, I write it to the output stream. And one of the interesting things that can be shown is that this order here is exactly the right order to do everything backwards in a backward traversal. So if you run to the one side and run to the back side, you have these streams in precisely the same order to write the data back and forth. So what you actually do is that you skip the requirement of having a fixed positions of your unknown in memory. So unknowns live in streams, and you do not write there is no fixed position, this unknown is written to that particular space in memory. You just live in streams, and that of course gives you the opportunity to add cells or delete cells when you refine or coarsen that. So in that way you can retain the Sierpinski order of the unknowns despite constant refinement and coarsening, and that is the idea on that. So this is dedicated to David actually. So how do we organize this in the software? So Oliver Meister, one of my PhD students, did a kind of a layer concept there. So you have a grid layer that does this grid modifications and traversal implementations. You have a hook layer. This hook layer for us is this kind of the first touch, last touch operators. Some edge appears on the first time, has to be read from the input stream. So all this logic is given on the hook layer. And then we have this kernel layer on top of it. And the kernel layer was inspired by Dune. So as in context of a project that we started for this in Stuttgart. Didn't finish so far, we'll have to see. And this has so-called volume and skeleton kernels. So a volume kernel would execute the element operator of a discretization scheme, and skeleton operators would have an edge, the two neighboring grid cells, and would kind of execute something like a flux computation on this. There are a couple of differences between our concept, because we cannot, as Jörn said in his talk, we cannot write to a grid cell that has already gone by in the stream. That doesn't work. We can always only write to one grid cell in the stream, so that gives a couple of restrictions, but they can typically handle it. Interesting from my point of view, consequence of this is sense of the lifetime of variables. So, for example, the typical unknowns in tsunami simulations, it's the water height, it's the momentum variables. So these are of course persistent, so they would be stored on stacks and streams. But things like residuals, flux variables, and so on are preferably non-persistent. So you would like to compute them on the fly and not store them permanently. So you might create them by a first touch hook and destroy them when they have been used by the last adjacent element. Would be just two such elements for an edge computation, for a flux computation. And otherwise you wouldn't store them or you would only like to store them on these intermediate color stacks, which are one-dimensional in nature and kind of small. So this is not totally possible, but at least to some extent possible. You have to store a couple of edges persistently. But for example, an interesting consequence is that we typically do not store old and new values of the unknowns. So you can overwrite unknowns by the new values when you write them to the output stream. So you do not have this unknown at time point n, unknown at time point n plus 1, and two sets of variables and maybe exchanging them after each type. So that's not what we have. So we have really an overwriting of the unknowns, and it's a consequence of really knowing when you touch an unknown for the last time. Yeah, I said I wanted to show a little bit on parallelization. We have actually two approaches for that. We have actually two approaches for many things, so it's resulting at the moment in two codes as well. So this is the code by Kavi Rahnema and Oliver Meister called Samoa. And there they perform a really classical cutting into equal-sized partitions thing. Space filling curve gives you uniform load balancing, gives you compact partitioning due to Hölder continuity that was shown by Gerhard Zumbusch, and kind of robust towards the changes of the grid. That works pretty well. And for our stack scheme, that means that we actually duplicate the stacks at partition boundaries. So we build up two boundary stacks at these partition boundaries during the traversals, and after the traversals you exchange these values. For example, you can write the normal components on these stacks that you need to do flux computations, and then you would do the flux computation on both sides again, as Robert said, but on both processors. Yeah, and it's kind of a dynamical ghost layer scheme. So you could interpret this as a kind of a ghost layer where the ghost layer is just written to the stack. But it's very similar in concept to a ghost layer. But you can kind of steer what values you really need to write on the stack. Yeah, I already said that. This is a very simple test scenario that we did, kind of a radial dam break problem, basic shallow water metal, finite volume, piecewise constant with Lax-Friedrich flux. So it's very simplistic, but it also provides kind of the lowest possible computational load. And we're at least not guilty of kind of covering bad scalability with heavy computational load per processor. So that's not, but what we can do really large simulations of that with really lots of millions of grid cells.
There's a nice result in there where you get to reload balance by just firing your stream to the next processor. Is that how that works? Kind of looks like it might.
Can you repeat the start?
So when you, because obviously you're doing dynamic load balancing there, right?
Yeah.
Does it fall out that the way you load balance is basically by transmitting a chunk of your stream to your neighbor? If you do much,
you kind of there's a couple of things you can do. You can just recompute the kind of from the total number of grid cells. You can say, okay, I need that many grid cells. I have this partition, and then I send everything else to neighbors. But you can also have something like a sharing. Say, I know the number of grid cells of my predecessor and my successor in the Sierpinski sequence, and then say, okay, I exchange half of the difference between these numbers. So that would lead like to a diffusion-oriented exchange of grid cells, and that doesn't give you an immediate exchange, but it was shown that usually at least in such simple settings, you see that the number of grid cells doesn't change that much from one step to the next. I mean, as I said, we want to do repartitioning after each second time step.
Yeah.
We want to do it pretty often, and then the number of cells doesn't change that often, and such a diffusion thing would be sufficient. Yeah, this is in principle not a bad result, but I really don't like. Well, you can guess what I don't like about the result. This is very apparent. There's a kind of a nasty kink at the 80 processors. Everything else is scaling well pretty nicely. So that's the speed up what we get on a kind of a pretty normal Nehalem cluster at the LRZ. This is a breakdown of these of that kink to the different phases in our computation. So you see it shows up in the computation and in preserving the adaptivity. So that's kind of the preserving conformity, and it doesn't show up in the load balance. So we didn't really find that, and at the moment we are restructuring the code. So don't really have an answer to that. Yeah.
You don't have any chance to have 8 boxes in a rack. that drop isn't suddenly when you go off.
With
off
10
track.
cores.
So you have 8 cores in each thing, and suspiciously
It happens
really
in a
good
similar
up-
way on another machine as well, so I don't think it's the machine. I would like to be the machine, but I have the. I really fear that it isn't.
What's the ratio of the load balancing compared to the numerics?
The load balancing is. It depends. The load balancing itself is cheap. Exchanging the values is cheap. What is more expensive is establishing the conformity. That is the bigger part.
So you iterate between processes there? Or?
Yeah. There's another approach that we started, which is oriented towards shared memory parallelization, which is done by Martin Schreiber on a different code, actually, as well. And there the idea is that you do parallelization in a tree-oriented way, and you cut off subtrees. And actually, his approach is that you cut off really many subtrees. So you kind of go down to sizes of maybe 1,000, 2,000 elements per subtree. And then you have, well, if you have couple of million grid cells, you have really much more such small subtree partitions than you would have cores. And then you schedule the partitions to the available cores in a dynamical way. So our goal is twofold. First, we want to tolerate imbalances in the computational load per element. So if we have, for example, when you look at Riemann solvers by Randy Levesque, they sometimes have a really different behavior on how much effort they spend for certain situations. For example, inundation situation can be much more difficult to compute. Also, same thing would happen if you have local time stepping, for example. There might be a different number of small elements in each grid, and this is really difficult to predict how much computational load you have per element. So this dynamical approach is kind of intended to deal with this, not knowing my exact computational load. And another point is, and that was the motivation on the project size, that we want to be able to tolerate a variable number of cores. So we want to be able to change the number of cores that we use throughout the computation, increase it when we have more load due to simulation. But it could also be, for example, that you say, I want to dedicate 2 or 3 cores or 1 core to writing an output, and go on computation at the same time, but with 1 core less. And this should be tolerated. And that is the idea behind that scheme. It's, as I said, a shared memory scheme. It turned out that the communication structure is much more easy because you have these simple kind of triangle-shaped partitions, because a subtree will geometrically be a triangle. You have easier migration of load between the well, now it's shared memory, that's easy as well, but it would also be easier if you go to MPI. And what we saw is that it's really difficult to have NUMA-aware scheduling, and we saw that, for example, threading building blocks is kind of able to handle this, but also we're showing up some problems with that. So this is a runtime speed-up result that we got. It's gone over a machine on a node that has 4 Intel 10 core machines that offer hyper-threading, so 2 threads per core. So we did this computations up to 80 cores, which you see that it doesn't really help you much going beyond the 40 cores, physical cores that you have. But you see that up to 20, 30 cores, we really get a nice result. And then there's a couple of things that impede us. So it might range from kind of NUMA effects that play a role that we can't really control yet, and other stuff. What's nice though is that if you look at this, at the coordinate here, that's mega triangles per second, million triangles per second. That's the throughput. So how many millions of triangles per second can you compute? And so it's 50 to 60 million triangles per second on a compute node, and I think that's a pretty large value in that sense. Yeah, this is an example we just recently submitted to the multi-core challenge. This is 4 simulations sharing the cores, and here you see that they, at different times, the simulations have different sizes, and they are assigned to with different number of cores. based on such a scheduling component that Martin implemented for this purpose. Yeah, a little bit on current and future work. So what we would like to do is go into this, so have adaptive simulations of kind of realistic problems. We have some first versions where you do the simulation, place some buoys, and well, I made it real small because it's really just an illustration yet. So we have lots of work to do to kind of improve the models. But that's what we want to do in the next months, to really see, okay, how does this adaptivity compare, for example, to what is done in GeoClaw in the software with block-oriented adaptive mesh refinement. And also a goal would be to obtain good scenarios for ensemble runs, like to see whether such a sharing of cores can give you a better overall throughput of when you do really a sequence or a parameter study also. Yeah, I will probably have to skip this and come back with kind of a summary. So we think that the structured adaptive bridge refinement will allow us to kind of simulate in a fully adaptive way, in a dynamical adaptive way, meshes with more than 1 million elements per core in a fast and efficient way. Goal is to maintain data locality with these space filling curves really on all scales. Memory, shared and distributed memory, using these space filling curves for the respective works and projects and software projects that we will do, so especially is a project ASCII, where we want to do coupled tsunami and earthquake events together with Jörn Behrens and Martin Käser and Louis Dahlgren, who are in the earthquake simulations and seismology fields. Yeah, and the other part I already mentioned. Okay, this is a couple of recent papers that we did on this. Yeah, thanks, and somehow in time.
Well, you said that you had a lot of time with the adaptation, and that because of the nature of your tsunami forecast, you had to do an adaptation every time step.
Yeah.
Tsunamis are incredibly predictable when they'll be in the neighborhood. Could you anticipate where you would need to do adaptation several time steps in advance with, say, a very coarse resolution, quick and dirty estimate of where the tsunami is likely to be, so as to save having to do the adaptation every time step?
We probably could. Maybe Jörn could comment on this better than me. From my opinion, I don't really care. So I would actually throw. I mean, that's a modeling point where I take anything that people throw at me. So our goal would be that we can, from a computational efficiency point of view, we are able to do the refinement and coarsening and load balancing as often as we wish, and that we're not forced to do it not as often as we can afford due to computational costs. So that would be my goal. If it turns out that I'm fine doing it less often, then we do it less often. But my primary goal would be to kind of open the possibility to really do it each time.
I mean, Matt talked about metric advection on Wednesday, and I guess it's metric wave propagation, but it's a sort of similar concept. There's a question over here.
Actually, I was just hoping you could flip over a couple slides back. You skipped a slide. I'll just that one.
That's something, actually, yeah, we had a master student programming this, so the motivation for us was that when you do the adaptive refinement and coarsening, so you need, for example, the bathymetry data when you refine. You want to have the bathymetry data for the refined cells. And rather than kind of keep this in our mesh and in whatever, we set up a server, parallel server that has the information on a local grid, and where you can just send in information, okay, give me the bathymetry at this coordinates, and you can also specify a level of detail when you say, okay, this resolution. And then the server will answer with that value, and the parallel server takes into account that when your partitions move to another point in space, you would need another part of the data. So the data is stored in a distributed way on your machine, and the patches of data automatically migrate to other processes, MPI processes, when you need them somewhere else. So all of this parallelization happens in the back. So it's kind of a nice idea, and we will see how it really helps. We haven't fully, it's just running since a month or so, but it's a nice idea that we wanted to test. And the diagram you see here is kind of an access pattern for actually a still sequential simulation. So you see here you have lots of bathymetry requests along a coastline, and this is not really visible. It's kind of a cone that is coming up, and this is this propagating wavefront in time. So this is so the vertical axis here is the time axis.
I could ask questions all afternoon, but I'm not going to subject you all to that. So should we break now for coffee, and we're going to recommence in half an hour?